Light is one of the most familiar phenomena in human experience. It allows us to see, to navigate, to measure time, and to explore the distant universe. Yet beneath this apparent familiarity lies a mystery so profound that it reshaped the foundations of physics and forced scientists to rethink the nature of reality itself. Among those who confronted this mystery with rare intellectual depth was Niels Bohr, whose calm, logical, and philosophical approach transformed how we understand both light and the limits of nature. To ask why the speed of light is the ultimate limit is not merely to ask a technical question about motion. It is to confront the structure of space and time, the meaning of measurement, and the way physical laws constrain what is possible in the universe. The story of this limit begins long before modern physics, in humanity's earliest attempts to understand light itself. For much of history, light was thought to travel instantaneously. When you lit a fire or saw a distant star, it seemed natural to assume that the illumination occurred at once. The idea that light might have a finite speed was counterintuitive. Only in the 17th century did scientists begin to test this assumption. Observations of Jupiter's moons by Olauer revealed subtle timing discrepancies that could only be explained if light required time to travel through space. This marked the first evidence that light does not move infinitely fast. Later, experiments by James Clerk Maxwell in the 19th century brought a deeper revelation. Maxwell unified electricity and magnetism into a single set of equations and discovered that electromagnetic waves propagate through space at a fixed speed. Remarkably, this speed matched the measured speed of light. Light, it turned out, is an electromagnetic wave. Its velocity is not arbitrary. It is dictated by the fundamental properties of electric and magnetic fields. At first glance, this seemed like a triumph of classical physics, but it carried a subtle implication that would eventually shake the foundations of science. Maxwell's equations predicted that light travels at a constant speed relative to the electromagnetic medium, often imagined as an invisible substance called the luminiferous ether. Physicists assumed that just as sound travels through air and water waves travel through water, light must travel through some physical medium. If this were true, then observers moving through the ether should measure different speeds of light depending on their motion. Experiments were devised to detect this effect. The most famous was conducted by Albert Michelson and Edward Morley in 1887. They sought to measure changes in light speed as Earth moved through the supposed ether. Yet no matter how precisely they measured, no variation appeared. Light's speed remained the same in all directions. This null result posed a crisis. If there was no detectable ether, how could light propagate? And more troublingly, why did its speed remain constant regardless of the observer's motion? This question led to one of the most revolutionary ideas in scientific history, Einstein's theory of special relativity. Einstein proposed that the speed of light in a vacuum is the same for all observers, regardless of how fast they are moving. This was not merely an experimental fact. Einstein elevated it to a fundamental principle of nature. To preserve this principle, space and time themselves had to change. Time could no longer be absolute. Two observers in relative motion would disagree on how long an event lasted and how far apart objects were. Length contracted, time dilated, and simultaneity became relative. The speed of light emerged as a universal constant, a boundary that nothing with mass could surpass. But while Einstein provided the mathematical framework, Niels Bohr contributed a deeper philosophical insight into what this limit means for knowledge and reality. Bohr was not content with equations alone. He sought to understand the conceptual foundations of physics, especially where classical intuition fails. Bohr's intellectual style was marked by restraint, patience, and a willingness to accept that nature may not conform to human expectations. Rather than forcing reality into familiar categories, he urged scientists to refine their concepts until they faithfully reflected experimental evidence. In the early 20th century, physics faced a second revolution, quantum theory. Light, once thought to be a continuous wave, revealed a particle, like nature in experiments, such as the photoelectric effect. Photons, discrete packets of energy, challenged the classical image of light as a smooth electromagnetic ripple. This duality between wave and particle behavior posed a profound conceptual problem. How could light behave like a wave in one experiment and like a particle in another? Bohr responded not by insisting on a single picture, but by introducing the principle of complementarity. According to this principle, certain properties of a system cannot be simultaneously described with full precision. Wave and particle descriptions are not contradictory, they are complementary. Each reveals a different aspect of a deeper underlying reality. This philosophical stance extended naturally to the speed of light. The constant velocity of light is not merely a technical parameter. It is woven into the structure of how we describe events, measure distances, and define causality. Light sets the ultimate speed at which information can travel. It establishes the boundary between what can influence what, shaping the causal order of the universe. To understand why light speed is a limit, one must examine the role of light in communication. Any attempt to transmit a signal, observe a distant object, or measure a remote event relies on electromagnetic radiation. Because this radiation cannot travel faster than light, no information can propagate more quickly. This ensures that cause always precedes effect in every inertial frame of reference. If faster than light communication were possible, paradoxes would arise. Observers in different states of motion could disagree on the sequence of events. An effect could appear to occur before its cause. The logical structure of time itself would collapse. The limit imposed by light speed preserves the consistency of causality. Bohr would emphasize that such constraints are not arbitrary. They reflect the deep coherence of physical law. The universe is not a chaotic collection of events, but an interconnected system governed by principles that maintain logical consistency across all frames of reference. Yet Bohr's approach cautions against assuming that we fully understand the underlying essence of these principles. In quantum mechanics, the act of observation influences what can be known. Measurements do not merely reveal pre-existing properties, they participate in defining them. This insight reshaped the philosophy of science. Similarly, the speed of light as a limit challenges our intuitive notions of motion and simultaneity. When we imagine traveling faster than light, we are extending classical ideas beyond their domain of validity. Bohr would argue that meaningful questions must be framed within the limits of the concepts that give them sense. If our conceptual framework breaks down at light speed, it is not nature that fails, but our language. Another foundation for understanding light speed lies in the nature of mass and energy. Einstein's famous relation, E equals mc squared, reveals that mass is a form of energy. As an object with mass accelerates toward light speed, its energy increases without bound. Reaching or exceeding light speed would require infinite energy. Thus the limit arises not from technological constraints, but from the structure of physical law itself. Photons, which have no rest mass, travel at light speed naturally. They cannot slow down, nor can they speed up. Their motion is not a matter of choice but of necessity. In this sense, light speed is not just a maximum velocity. It is a defining property of massless particles and the spacetime through which they move. Bohr would interpret this not as a mechanical limitation, but as a manifestation of deeper harmony in nature. The constants of physics, including the speed of light, appear finely tuned to allow stable structures, atomic matter, and coherent laws. They provide a stable framework within which complexity and understanding can emerge. At the atomic scale, Bohr's own model of the atom demonstrated how quantized energy levels prevent electrons from spiraling into the nucleus. Stability in nature arises from discrete rules rather than continuous freedom. Likewise, the cosmic speed limit provides stability at the largest scales, ensuring that energy, matter, and information remain governed by consistent relations. The background to light speed as a limit therefore spans centuries of scientific development, from early speculation about instantaneous illumination, to Maxwell's electromagnetic theory, to Einstein's relativity, and finally to Bohr's philosophical interpretation of quantum reality. Each step deepened our understanding of both light and the nature of physical law. This foundation reveals that the speed of light is not an arbitrary cap imposed by engineering difficulty or incomplete knowledge. It is embedded in the fabric of spacetime, in the structure of causality, and in the logic of measurement itself. In the next part, we will move beyond historical and conceptual groundwork into a deeper scientific exploration. We will examine how relativity mathematically enforces the light speed limit, how spacetime geometry explains this boundary, and how quantum theory intertwines with these ideas at the most fundamental level. For now, we pause with a recognition that the speed of light is not merely a number. It is a principle that shapes reality, a boundary that preserves coherence, and a reminder that nature often requires us to revise our deepest intuitions in order to understand it. To understand why the speed of light stands as an unbreakable limit, we must move from historical foundations into the mathematical and physical structure of spacetime itself. The limit does not arise from mechanical resistance or technological inadequacy. It emerges from the geometry of reality, from the way space and time are interwoven, and from the internal logic of relativistic and quantum laws. At the core of this understanding lies Einstein's special theory of relativity. Its starting point is deceptively simple. The laws of physics are the same in all inertial reference frames, and the speed of light in a vacuum is constant for all observers. These two statements alone force a radical reconstruction of our intuitive picture of the universe. In classical physics, velocity adds in a straightforward way. If a train moves at 50 kilometers per hour, and a person walks forward inside the train at 5 kilometers per hour, an outside observer sees the person moving at 5 kilometers per hour. If this logic were applied to light, then an observer moving toward a beam should measure light traveling faster than another observer standing still. Yet experiments show that this does not happen. Light speed remains fixed. To reconcile this, space and time must adjust. Distances contract along the direction of motion. Time dilates, meaning moving clocks tick more slowly than stationary ones. Events that appear simultaneous to one observer may not appear simultaneous to another. These effects are not illusions or distortions. They are direct consequences of the structure of spacetime. Mathematically, this structure is described by Lorentz transformations. These transformations replace the classical Galilean transformations and preserve the speed of light as an invariant quantity. They define how space and time coordinates transform between observers moving at constant velocities relative to one another. The invariance of light speed becomes a geometric property of spacetime itself. In this framework, the speed of light functions not merely as a velocity, but as a conversion factor between space and time. It links spatial distance and temporal duration in a single four-dimensional continuum. When we write distances in spacetime, time is multiplied by the speed of light to place it on equal footing with spatial dimensions. This reveals that light speed defines the fundamental scale at which space and time merge. One of the most profound implications of relativity is the structure of the light cone. For any event in spacetime, there exists a region of possible future events that can be influenced by it, and a region of past events that could have influenced it. These regions are bounded by the speed of light. Signals traveling at or below light speed can connect events within the light cone. Events outside this cone are causally disconnected. This geometric structure enforces causality. No physical influence can propagate faster than light without breaking the causal order of events. Faster than light travel would allow signals to move outside the light cone, enabling effects to precede their causes in some reference frames. Such violations would undermine the logical coherence of physical law. From another perspective, the limit arises from energy and momentum. As an object accelerates toward the speed of light, its relativistic momentum increases dramatically. The closer it approaches light speed, the more energy is required to produce further acceleration. This is not a matter of friction or resistance, but a consequence of the way energy transforms with velocity. The relativistic energy of a particle with mass is given by a relation that diverges as velocity approaches light speed. In practical terms, this means that no finite energy supply can accelerate a massive object to or beyond the speed of light. The boundary is absolute. Massless particles, such as photons, obey a different rule. They cannot be brought to rest, nor can they exceed light speed. Their energy is entirely kinetic, and their motion through spacetime always occurs at this invariant velocity. In a sense, light speed is not something photons achieve. It is what they are. Spacetime itself enforces this constraint. In relativity, motion is not merely movement through space, it is movement through spacetime. All objects travel through spacetime at a constant total rate. Objects at rest in space move entirely through time. Objects moving rapidly through space move more slowly through time. Photons, traveling at light speed, experience no passage of time at all in their own frame. This reveals a subtle but powerful insight. Light speed is not a special case among velocities, it is the boundary between time-like and light-like motion. Below it, objects have rest frames and experience time. At it, objects lose the concept of rest and time becomes undefined in the conventional sense. Above it, the mathematical structure would imply imaginary time intervals and reversed causal order, signaling a breakdown of physical meaning. Bohr would caution that these results reflect the limits of our conceptual categories. The mathematics does not merely describe motion. It encodes the conditions under which concepts such as time, causality, and identity remain meaningful. At the quantum level, the role of light speed becomes even more intricate. Quantum field theory describes particles not as isolated objects, but as excitations of underlying fields that permeate space. These fields obey relativistic constraints. Interactions propagate at or below the speed of light, ensuring that quantum processes remain consistent with relativistic causality. Virtual particles in quantum interactions may appear to momentarily exceed light speed in mathematical formulations, But no measurable signal or information travels faster than light. The underlying theory preserves causality in all observable phenomena. One might ask whether quantum entanglement violates this limit. Entangled particles exhibit correlations that appear instantaneous, regardless of distance. Measuring one particle immediately determines the state of the other. This phenomenon has sometimes been described as faster than light influence. Yet Bohr's interpretation of quantum mechanics provides a resolution. Entanglement does not transmit usable information faster than light. Instead, it reflects a holistic description of a shared quantum state. The correlations become meaningful only when measurement results are compared through classical communication, which remains limited by light speed. Here again, complementarity plays a role. The quantum system cannot be fully described as a collection of independent particles with definite properties. It must be understood as a unified whole whose observable outcomes depend on measurement context. The apparent paradox dissolves when we recognize the limits of classical language in describing quantum reality. General relativity extends these ideas by showing that gravity itself arises from the curvature of spacetime. Mass and energy distort spacetime geometry, influencing the paths of particles and light. Even in this curved geometry, the local speed of light remains constant. Gravity can bend light's trajectory, delay its travel time, or trap it within black holes, but it does not allow light to be locally surpassed. Near a black hole, spacetime curvature becomes extreme. The escape velocity at the event horizon equals the speed of light. Beyond this boundary, even light cannot escape. This is not because light slows down, but because spacetime itself tilts inward so steeply that all future paths lead deeper into the gravitational well. In this context, light speed functions as the threshold between escape and confinement, between accessible and inaccessible regions of spacetime. It defines horizons beyond which information cannot reach distant observers. The cosmic expansion of the universe introduces another subtlety. Distant galaxies can appear to recede from us faster than the speed of light due to the expansion of space itself. However, this does not violate relativity, because the galaxies are not moving through space faster than light. Rather, space itself is stretching. The local speed of light remains inviolate. This distinction reinforces a key point. The limit applies to motion through spacetime, not to the global behavior of spacetime geometry. Relativity constrains local velocities and causal influences, while allowing the universe's large-scale structure to evolve dynamically. From a field-theoretic perspective, the speed of light emerges as the maximum propagation speed of disturbances in fundamental fields. Any interaction, whether electromagnetic, gravitational, or nuclear, propagates at or below this speed. This ensures a universal causal structure across all forces. One can think of the speed of light as the maximum rate at which reality can update itself. It defines how quickly changes in one region can affect another. Without such a limit, the concept of localized events would dissolve, and the notion of independent physical processes would lose meaning. Bohr's philosophical insight emphasizes that physical theories are not merely mirrors of reality, but structured languages for describing experience. The constants and limits they contain, including the speed of light, define the conditions under which coherent description is possible. If no speed limit existed, observers could not agree on the sequence of events. The distinction between past and future could blur. Measurement outcomes could not be consistently ordered. The framework of scientific explanation would fracture. Thus, the light speed limit is not simply a barrier to faster travel. It is a cornerstone of intelligibility. It stabilizes the logical architecture of physical law and preserves the consistency of observation. As we reflect on these deep scientific principles, we see that the limit arises simultaneously from geometry, energy, causality, and quantum structure. It is woven into every layer of modern physics, from the smallest scales of particle interactions to the largest scales of cosmic evolution. In the next part, we will move beyond technical explanation and explore the broader meaning of this limit. We will examine what it implies for human understanding, the nature of reality, and the philosophical insights inspired by Bohr's vision. We will consider how the speed of light challenges our intuitions about time, knowledge, and the boundaries of what can be known. The speed of light is not merely a scientific constant. It is a philosophical boundary, a conceptual frontier, and a profound lesson about the nature of knowledge itself. When examined through the intellectual lens of Niels Bohr, it becomes clear that this limit does more than constrain motion. It shapes how reality can be observed, understood, and meaningfully described. At first, the idea of an ultimate speed limit may feel like a restriction imposed upon human ambition. We imagine faster spacecraft, instantaneous communication, or boundless freedom of movement. Yet Bohr would remind us that limits are not simply barriers, they are conditions of coherence. Without certain constraints, meaningful structure dissolves. In physics, limits often serve as organizing principles. The uncertainty principle limits what can be known about position and momentum, yet this limitation enables stable atomic structure. Quantization restricts energy values, yet this restriction prevents matter from collapsing. Similarly, the speed of light restricts motion and information flow, yet this restriction preserves causality, consistency, and intelligibility. To grasp the deeper meaning of this limit, we must confront the relationship between observer and reality. In classical thinking, the world was assumed to possess definite properties independent of observation. Light speed challenges this assumption by tying measurement to the finite transmission of information. We do not observe events as they occur, we observe them as their light reaches us. Every astronomical image is a glimpse into the past. When we see a distant galaxy, we are not seeing it as it is now, but as it was millions or billions of years ago. The speed of light imposes a temporal separation between reality and perception. Our knowledge of the universe is therefore inherently historical. Bohr would emphasize that this is not a flaw in observation, but a fundamental feature of how knowledge is structured. The act of knowing is constrained by the physical means through which information travels. Light speed defines the horizon of what can be known at any given moment. This has profound implications for how we think about simultaneity. Two events that appear simultaneous to one observer may not appear simultaneous to another moving relative to them. There is no absolute universal present moment. Instead, each observer carries their own slice of spacetime. The idea that time itself depends on perspective challenges deeply rooted intuitions. Yet Bohr's philosophical approach encourages us to accept that intuition must sometimes yield to evidence. Concepts that once seemed self-evident may require revision when confronted with experimental reality. The light speed limit thus teaches humility. It reminds us that human perception evolved for survival, not for comprehending the deepest layers of physical law. When nature behaves in ways that defy common sense, it is not nature that must change, but our conceptual framework. Beyond measurement, the limit reshapes our understanding of cause and effect. In everyday experience, causality feels immediate and local. We flip a switch and a light turns on, yet beneath this apparent immediacy lies a chain of signals propagating at finite speed. At cosmic scales, the separation between cause and effect becomes dramatically evident. The light from an exploding star may travel across space for millennia before reaching Earth. By the time we observe the event, it has long since concluded. The universe unfolds on timescales far beyond direct human experience. The speed of light therefore partitions reality into regions of influence. Some events lie within our causal reach, while others are forever beyond it. The observable universe itself is bounded by how far light has traveled since the beginning of cosmic time. There exist galaxies whose light will never reach us, not because they do not exist, but because spacetime expands faster than their light can cross the distance. This introduces a subtle existential insight. There are truths about the universe that may remain forever inaccessible, not due to ignorance or lack of intelligence, but due to the fundamental structure of spacetime. Knowledge has horizons. Bohr would argue that this does not diminish the value of scientific inquiry. Instead, it clarifies its scope. Science does not aim to describe an unreachable absolute reality, but to construct coherent and testable descriptions of observable phenomena within defined limits. The speed of light also challenges our understanding of identity and continuity. In relativity, an object's length depends on its motion. Its clock ticks at a different rate depending on its velocity. Even the order of events in its history can vary between observers. This means that there is no single universal narrative of what happens. Instead, there are multiple consistent perspectives, each valid within its frame of reference. Reality becomes relational rather than absolute. Bohr's principle of complementarity resonates deeply with this idea. Just as wave and particle descriptions offer different yet compatible accounts of quantum behavior, different spacetime perspectives offer complementary descriptions of events. No single viewpoint exhausts reality. This insight extends beyond physics into philosophy and epistemology. Human understanding is always situated. Every description depends on context, perspective, and the conceptual tools employed. The speed of light, by enforcing relativistic effects, makes this dependence explicit. It also reshapes our intuition about motion and effort. In classical mechanics, speed feels like something that can be increased indefinitely with sufficient force. Relativity reveals that speed approaches a boundary that cannot be crossed. Progress slows as the limit nears, requiring ever greater energy for diminishing returns. This can serve as a metaphor for intellectual pursuit. As knowledge advances, deeper understanding often demands greater conceptual refinement rather than simple extension of old ideas. Some boundaries cannot be overcome by brute force. They require rethinking the nature of the problem. The light speed limit further influences how we think about communication. No message can travel faster than light. This means that no matter how advanced technology becomes, instantaneous communication across vast distances remains impossible. Even a civilization spanning galaxies would experience unavoidable delays. In a philosophical sense, this enforces a form of cosmic solitude. Each region of the universe unfolds partly independent of others, limited by the finite speed at which information travels. The universe is unified, yet not instantaneously interconnected. Bohr's perspective would interpret this not as fragmentation, but as structured coherence. Locality allows systems to maintain individuality while still participating in a larger cosmic order. Without such limits, distinctions between regions could dissolve, and meaningful structure might collapse. Another implication lies in the relationship between determinism and freedom. If information could travel infinitely fast, the entire universe could be instantaneously correlated. Every event might be immediately constrained by all others, leaving little room for localized autonomy. The light speed limit introduces a form of causal insulation. Events unfold within bounded regions of influence, allowing complexity, diversity, and emergent behavior to arise. Stars form, planets evolve, life emerges, and consciousness develops within causal neighborhoods rather than under universal instant control. This boundary thus supports the richness of cosmic evolution. It enables systems to explore possibilities without being instantly overridden by distant influences. In quantum theory, the interplay between non-local correlations and relativistic limits further deepens this picture. Entangled particles share correlations across distance, yet cannot transmit usable information faster than light. Nature permits profound interconnectedness while preserving causal structure. Bohr would emphasize that this delicate balance reflects the subtle harmony of physical law. Reality allows relationships that transcend classical separability, yet maintains boundaries that preserve coherence and prevent paradox. The speed of light also shapes our understanding of time's arrow. Because information cannot travel backward faster than light, the causal chain maintains a forward direction. Entropy increases, events unfold, and memory accumulates in a consistent temporal order. If faster than light influence were possible, temporal order could become ambiguous. Effects could precede causes in some frames, undermining the distinction between past and future. The light speed limit stabilizes time structure. This stability allows narrative, history, and experience to exist. Human consciousness depends on ordered sequences of events. Without a consistent temporal framework, memory and meaning would dissolve. From a broader philosophical perspective, the speed of light embodies a principle of moderation. It represents a balance between possibility and constraint. It permits immense speed, vast communication, and cosmic connection, yet prevents logical contradiction and causal chaos. Bohr's intellectual temperament favored such balance. He resisted simplistic extremes and sought nuanced frameworks capable of accommodating complexity. The light speed limit exemplifies this balance by allowing extraordinary phenomena while preserving conceptual coherence. It also challenges humanity's aspiration toward absolute mastery. We may dream of transcending all limits, but nature reminds us that some boundaries are intrinsic to the structure of reality. Wisdom lies not in denying these boundaries, but in understanding their role. In this sense, the speed of light becomes a philosophical teacher. It teaches patience, humility, and respect for the underlying order of the universe. It invites us to refine our questions, adjust our expectations, and deepen our conceptual tools. Rather than asking how to break the limit, Bohr might encourage us to ask why the limit exists and what it reveals about the nature of knowledge. What does it mean that information has a maximum speed? What does it imply about the relationship between observer and observed? How does it shape the language with which we describe reality? The answer is not merely technical. It touches on the foundations of epistemology. Our descriptions of the world are constrained by how information reaches us. We cannot step outside spacetime to observe it from an external vantage point. We are participants within the very structure we seek to understand. This participatory role is central to Bohr's philosophy. Measurement is not a passive recording of pre-existing facts, but an interaction that defines what can be meaningfully said. The light speed limit constrains this interaction, shaping what can be observed and how observations relate. Ultimately, the limit forces us to confront the idea that reality is not fully accessible from any single perspective. It invites intellectual humility, while opening space for creative theoretical insight. In the final part, we will bring these reflections together into a broader conclusion. We will explore how the speed of light influences humanity's future, our cosmic perspective, and our ongoing search for meaning within the universe. We will reflect on Bohr's legacy and consider how his calm, philosophical approach can guide us in confronting the deepest limits of knowledge.